In recent lessons, you've learned about the components of electrochemical cells and how these components interact with each other while charging and discharging a battery. In this lesson, you will learn about the actual chemicals that are used inside of the negative and the positive electrodes in order to optimize how a battery cell works. In particular, when we're designing a battery cell, we desire to have high specific energy and high energy density. Now, specific energy has to do with how much energy we can store per unit volume, and energy density has to do with how much energy we can store per unit mass. So we would like to have as high a specific energy and energy density as possible for many applications, especially portable applications, which will mean that we would like to reduce volume, reduce mass, and increase energy. We also desire high specific power and high power density. Specific power has to do with how much power I can pull out of a battery per unit volume, and power density is how much power I can get per unit mass. Power is the rate at which we use energy. And so the energy capacity of a battery cell tells me how much work I can do in total, and the power capability says how quickly we can pull that energy out to do work. We also desire that our solution be low cost and have long life and have low toxicity and have high recyclability. High energy and high power capabilities of battery cells depend on an overall maximum cell voltage and an overall maximum cell current. Remember that voltage multiplied by current equals power, and voltage multiplied by current multiplied by time equals energy. So if I can maximize a cell's voltage and maximize the current that we can extract from that cell, we're going to be able to maximize these metrics. And ultimately, how much voltage I get out of a battery cell depends on the specific materials that I use in the electrodes, and how much current I get out of the battery cell usually depends on how the cell is constructed. In order to talk about battery cell voltage, we must first understand electrode potential. The propensity of or a natural inclination of one material to gain or lose electrons in relation to another material is known as its electrode potential. Compounds that have negative values for electrode potential with respect to some reference material are used for negative electrodes. And compounds that have positive values of electrode potential with respect to some reference are used for positive electrodes. And the larger the difference between the electrode potentials in the negative and positive electrodes, the greater the voltage that will be developed by the cell, and hence the greater the amount of energy that can be stored by the cell, everything else being equal. So it would be really nice if we could somehow tune the electrode potentials arbitrarily to be anything we wanted, but we in fact cannot do that. We have to work with the materials supplied to us by nature, and these are the elements in the periodic table. So the periodic table is a very powerful visual device for thinking about all of the elements found in nature. So we're going to spend a few minutes discussing how this table is organized. One of the important aspects of the table from our point of view is that the relative reducing and oxidizing capabilities of the elements are indicated by the arrow that is drawn underneath the table. In particular, you can see that the strong reducing elements are grouped on the left-hand side, and that the strong oxidizing elements are grouped on the right-hand side of the table. So I might consider building a battery cell that has a negative electrode using an element from the left of the table and some positive electrode using an element from the right side of the table. And in fact, one of the most promising future technologies is known as lithium air. At this point in time, there are still quite a few developmental difficulties to be overcome before a real practical lithium air battery is a commercial success. But a lithium air battery could have one of the greatest energy and power densities of any known combination of elements at this point. A lithium air battery uses a negative electrode that's built from solid lithium metal, and you can see lithium in the far left-hand column of the table, from the second from the top. The positive electrode in a lithium air battery is oxygen that's harvested or scavenged from air, and you can see that oxygen is near the top right of the table. In general, however, lithium air or not, whenever we build an electrochemical cell, we desire to use elements from the far left and the far right of the table whenever possible, and as we'll see shortly, as far to the top of the table as possible, because that will end up with less weight, less mass. Let's take a look at a portion of this periodic table in a little bit more detail. The diagram that I've put on the slide zooms in on the top left part of the periodic table, so it's easier to see some of the details. Every element, whether it's human-made or if it's found in nature, has its own box in the table, and each one of these boxes lists quite a lot of information about that element. In the left column of each box, you can see that there's an integer number on top, then a symbol, then a name, and then a real valued number. To the right of the box, there's a sequence of integers. And you can also see that the symbols in the boxes themselves are color-coded, and all of this has meaning. So let's spend a few minutes looking at what all of these details mean. First, the integer number that's listed on the top left of each box is known as the atomic number of the element. The atomic number is equal to the number of protons in the nucleus or the core of the atom of that particular element. Underneath the atomic number, you can see the symbol that's used for that element when it's listed in a chemical formula. In this table, the symbols are color-coded. The coloring tells you whether the element is a solid or a liquid or a gas at room temperature. If the element is a solid, the symbol will be black. If it's liquid, the symbol will be blue. And if it's a gas, the symbol will be red. Next, the full element name is listed underneath the element symbol. And underneath the element name, you can find the mean atomic weight. Now, the atomic weight of an atom is equal to the weight of all of its protons plus the weight of all of its neutrons plus the weight of all of its electrons. But the weight of an electron is really tiny compared to the weight of a proton or a neutron, and so it really doesn't have much impact on the mean atomic weight. So you can think of the mean atomic weight as being the average number of protons plus neutrons found in that element in nature. And while every element of the same type has exactly the same number of protons, which makes it that element, there is some variability in the number of neutrons that is found from sample to sample. And that's why this is a mean or an average atomic weight and not an exact atomic weight. Mean atomic weight is also equal to the number of grams per mole of that element. In chemistry, a mole of a material is equal to 6.022 times 10 to the power 23 units of that material. This unit is defined in such a way that 1 mole of protons is exactly equal to 1 gram in mass. And also 1 mole of neutrons has mass exactly equal to 1 gram. And the conversion factor, which is a somewhat unusual number, but 6.022 times 10 to the 23rd power, is known as Avogadro's number. Finally, the list of numbers on the right-hand side of the box indicates the number of electrons in each electron shell of that element. Describing where electrons exist in relation to the nucleus of an atom is actually quite a complicated subject, and it involves quantum mechanics. But for this course, it will be sufficient to think of the element in terms of a classic model where there are shells surrounding the nucleus, and each shell is capable of holding electrons. So each shell has a maximum number of electrons that it can hold, and this number depends on the distance of this shell away from the center of the atom. If you've studied quantum mechanics, you know that this model isn't quite right, but whether using the quantum model or the classical model, an electron shell corresponds to a possible set of electron energy levels. Continuing with our discussion of the entries of the periodic table, it turns out that the background color of each box in the table is also meaningful. It indicates whether the element is a metal or a non-metal, and if it's a non-metal, of what kind, or whether it's a metalloid. The organization of the table is important. The rows of the table are called periods. All elements that have that share the same row are in the same period and have the same number of electron shells. Therefore, we can say that the row or the period of an element is equal to the number of electron shells surrounding the nucleus of that element. The columns of the table are called groups, and all elements in any group generally have the same number of valence electrons, where valence is a special name given to the outermost shell. There are exceptions to this last rule, and the transition metals in the center of the periodic table often act a little bit strangely, and sometimes they do exactly follow this rule and sometimes they do not, which is one good reason to have these numbers listed in the top right of the box to tell you how that element actually behaves. So as we've just seen, elements within each individual group or column of the table have the same number of valence electrons except for some special cases with transition metals. It turns out that the number of an element's valence electrons allows us to predict how that element will interact and react with other elements. So all elements that share the same particular group tend to have similar chemical properties. When the outermost electron shell is full, as is the case with all of the noble gases on the very far right column of the periodic table, then there are no free electrons available to take part in a chemical reaction. And so the noble gases are chemically non-reactive, and this condition is something we call inert. Noble gases are inert. But for some other examples, I've drawn the electron shells for 3 different elements. On the left, I've drawn lithium. And if you look at the periodic table, you notice that lithium has an atomic number of 3, which means that it has 3 protons in its nucleus, and the nucleus has a +3 charge. So for the lithium atom overall to be charged neutral, it must have 3 electrons. The first electron shell can hold a maximum of 2 electrons, so that there are actually 2 electron shells, and this remaining third electron is in the second shell, and that's the valence electron. In the center, I've drawn carbon. Carbon has an atomic number of 6, which means that it has 6 protons in its nucleus, so the nucleus has a net positive charge of +6, and to balance that we need 6 electrons. So as with lithium, 2 of these electrons exist in the centermost shell, and the remaining 4 electrons fit in the second shell. And since carbon needs only 2 shells of electrons, the second shell is the valence shell, and there are 4 electrons in the valence shell. And finally, I have drawn cobalt, which has an atomic number of 27, so there are 27 protons, and to be charged neutral, there must be 27 electrons. And I've drawn the electron shell configuration here for cobalt, and you can see that in the outermost shell, there are 2 electrons, so we say that cobalt has 2 valence electrons. So I chose these 3 elements not completely at random, but because they turn out to be extremely common in lithium-ion battery cells. You might imagine lithium to be an important element, given the name lithium-ion battery cell, but you might not know that carbon and cobalt are also really important. It turns out that the negative electrodes of most lithium-ion battery cells are made from some form of carbon, and it turns out that the positive electrodes of many lithium-ion battery cells contain a fair amount of cobalt. Thinking a little bit more about the valence electrons and how elements having the same number of valence electrons are listed in the same column of the table, we can talk about these groups as having similar chemical properties. So in the far left of the periodic table, we have the elements that are known as the alkaline metals. These are the group 1 elements, and they have only 1 valence electron. On the far right of the periodic table, we have the noble gases in group 18, and these are chemically inert, so they don't interest us very much in this course. However, in the column just before that, we find the halogens in group 17, which are lacking only 1 valence electron before that valence shell is completely filled. And it turns out that elements that have only 1 or 2 valence electrons are highly reactive because these electrons are very easily removed and cause the atom to become a positively charged ion. And these atoms are shown in the left 2 columns of the periodic table, and they're very strong reducing agents because these extra electrons are quite easily donated and becoming oxidized themselves. I use the term redox here, and this might be the first time I've used that term in this course. Redox is a term that's commonly used to describe any chemical reaction that involves the exchange of electrons. And redox is simply a shortened form of reduction oxidization. You put those together and you get redox. On the right side of the table, ignoring the noble gases, we see the elements that are lacking only 1 or 2 electrons before their valence shell is filled. And these are the strongest oxidizing agents because they have this deficit of valence shell electrons, and they strongly desire to steal or maybe accept electrons in a redox reaction, becoming reduced themselves. The energy level of an atom is determined by the configuration of electrons into shells. We talked in the last lesson about electrochemical potential energy. Well, this is how that energy is stored. It's by changing the configuration of electrons in shells. And so an atom's energy level can be changed by moving an electron from one shell to another shell, or by gaining or losing electrons from its valence shell. Most fundamentally, a battery stores this electrochemical potential energy by changing this configuration of electrons, as I said, in the electron shells in its electrode materials. So when charging a battery cell, the electrons move to higher energy configurations in both electrodes, and when discharging, the electrons move to lower energy configurations in both electrodes. The difference in electrical potential energy before and after an electrochemical reaction can be measured using a voltmeter because the voltage differences in the species before and after the chemical reactions are these changes. It's a direct measure. And electrochemists over the years have very carefully studied the difference in electrical potential energy before and after reactions for thousands and thousands of different reactions under highly regulated conditions. And these results have been recorded in tables that are called electrochemical series. And these are arranged according to the electrode half reaction standard potentials, denoted E with a superscript 0. So to clarify, battery cells undergo a full reaction that comprises 2 half reactions. The half reaction is what happens at one electrode. So a negative electrode has one half reaction and a positive electrode has a separate half reaction. And because it's possible to somewhat arbitrarily build your battery cell by choosing an electrode reaction for the negative electrode and a different one for the positive electrode, it's more convenient actually to list the half reaction potentials than it is to list all of the possible combinations, which would make for a much larger table. And so we can use these half cell reactions to compute what the total voltage of the cell is, as we'll see. The table to the right of the slide shows a short example of what an electrochemical series looks like. The top row shows the chemical reaction of a positively charged lithium ion plus a negatively charged electron becoming a charged neutral lithium. More specifically, the subscript AQ informs us that this lithium cation is in aqueous solution, which means that it is dissolved in water. And the subscript S informs us that the product lithium will be in solid metallic form. This half reaction is said to have an electrode standard potential of negative 3.04 volts. Now, voltage is a property that must be measured with respect to a reference. There's no such thing as an absolute voltage. So instead, there's a potential difference between 2 spatial locations that somehow can be measured. So in order to measure and tabulate standard potentials, we must establish some reference potential against which we measure all of the standard potentials that we're interested in finding. And in this table, the reference half reaction is shown in the 4th row. In this row, we see that 2 positively charged hydrogen cations plus 2 negatively charged electrons become hydrogen gas. And we see that this electrode reaction has a standard potential of 0 volts. And that's simply because we defined it to be this way. All other reactions are measured with this as a reference. And unfortunately, the laboratory setup and procedure for making this measurements is something that's quite interesting, but it's beyond the scope of what we really need to know in this course. So I suggest, if you're interested, that you look up a course in electrochemical methods. The numeric values in the electrochemical series are known as the standard reduction potentials of the reaction. Lithium at the top of the list has the most negative value, which indicates that it's the strongest reducing agent in this table. Fluorine, on the other hand, at the very bottom of the table is the strongest oxidizing agent because it has the largest positive value for its standard potential. So if we were to construct a battery cell where the negative electrode were lithium and the positive electrode was fluorine, we would be combining the half reaction from the top row and for the negative electrode and the half reaction from the bottom row for the positive electrode. And the cell nominal voltage then would be equal to the reduction potential of the positive electrode minus the reduction potential of the negative electrode. So in this example, the cell voltage would be 3.87 volts minus negative 3.04 volts, which gives us 5.91 volts. Now, I doubt you've ever seen a battery cell that's rated with a nominal voltage even close to 6 volts. And the reason is not because we don't know how to make electrodes for such a cell. In fact, we can just pull them out of this table. Instead, the reason is that we don't know how to make an electrolyte for that cell. There's presently no known electrolyte that will withstand this kind of a voltage without decomposing. So in summary, if we desire high specific energy and high specific power, then we desire light elements which come from near the top of the periodic table. If we desire high voltage, then we want to use strong oxidizing agents paired with a strong reducing agent so that one has an excess of valence electrons and the other has a small deficit of valence electrons, and that these match up together. Because the strengths of the oxidizing and reducing natures, this will result in a cell that has high voltage. Of course, these are not the only considerations when we're designing a battery cell. One thing that you learned in the previous slide was there needs to be an electrolyte that can support this voltage that's developed between the electrodes. We also require, of course, that the solution be low cost, which means that we need to use elements that are abundant in nature and which are easily isolated from whatever basic compounds we extract from the earth. Further, we desire that the battery cell has long life and low toxicity, and that it has high recyclability. So there are scientific aspects to cell design, as we've seen, but there are also economic and environmental aspects that need to be considered as well. And jointly optimizing all of these considerations makes for a very interesting design problem.